In our previous videos, you learned about the basics of transistors and how we can amplify a signal with them. But there's a lot more we can do with transistors, from building current sources over duplicating a current to band-gap voltage references. Join us again for more transistor circuits. A current source can deliver a preset output current, regardless of its output voltage. Transistors can be used to build a circuit which behaves like a current source. All we need is a voltage source, resistors, and of course a transistor. For this example, we will use an NPN bipolar transistor. We wire them like this and analyze how the circuit works. The voltage source provides a constant voltage which is high enough to forward bias the base emitter diode of our bipolar transistor. Assuming a constant base emitter voltage VBE of 0.6 to 0.7 volts, we can calculate the voltage at the resistor RE. The current IRE flowing through this resistor equals VB minus VBE over RE. If the voltage VB remains constant, so does the current IRE. The base current is obtained via the current gain beta. With the currents flowing through base and emitter, we can solve for the collector or output current, Iout, which equals IRE times 1 minus 1 over beta. The last term, 1 over beta, can be neglected and we can state for the output current Iout equals IRE. This current does on first glance not depend on the load RL, which meets the requirements of a current source. We can also adjust the output current by either changing the voltage VB or the resistor RE. But the circuit has its limits. The voltage at the output Vout must not drop below a certain minimum voltage. Otherwise, the bipolar transistor no longer operates in the active regime but in saturation. And the output characteristic of our current source might look like this. In saturation, the bipolar transistor shows strong variations of collector current with respect to its collector-emitter voltage. We can translate this to a minimum and maximum load resistance for our current source. While the current source has no problem handling a short as its load, there is a maximum resistance we are allowed to connect to the output. The lower boundary for the output voltage is governed by the saturation voltage of our bipolar transistor. This means the minimum collector-emitter voltage for which the bipolar transistor operates in the active regime. So we can calculate the minimum output voltage. Hence the voltage VB influences the output current and the minimum output voltage. Besides the minimum output voltage, another crucial quantity for our current source is output current stability. We could ask how much the output current changes when we manipulate the applied output voltage. Of course, we want this change to be as small as possible. Part of this change can be seen in the output characteristic of our bipolar transistor. If the collector-emitter voltage changes, so does the collector or output current. To circumvent this problem, we try to stabilize the collector-emitter voltage. When we achieve a constant output current, also the voltage drop over RE is constant and the potential at the emitter is stabilized. Thus, it is sufficient to pin the potential at the collector of our current controlling transistor. To do so, we just add another bipolar transistor to our circuit. Any change in output voltage changes the collector-emitter voltage of the second transistor T2. The collector-emitter voltage of the current controlling transistor T1 is pinned to VCE1 equals VB2 minus VBE2 minus VRE. The second base voltage VB2 is selected in such a way that the lower transistor T1 operates in the active regime, just like it did in our previous circuit. We already calculated the lower boundary for the voltage at the collector of T1. We add the base emitter voltage of T2 and get the minimum second base voltage VB2. By adding transistor T2, we decrease the change of output current as a result of varying output voltage. But we have to trade the minimum output voltage of our circuit for a more stable output current, as also T2 must operate in the active regime. This circuit is known as a cascade current source. Generating a current is a nice thing, but especially in integrated circuit design, circuit performance depends on the relation between two quantities and less on their absolute values. And here lies the problem for our current source. Creating two individual current sources with equal current is a challenging task, as all involved devices must perfectly match their counterpart in the second current source. Fortunately, there's a small circuit which can solve our problem, the current mirror. The current mirror consists of two transistors with their base terminals connected to each other. One of the transistors has its collector wired to the base, transforming it into something like a diode. If we force a current through this transistor, its base emitter voltage VBE1 will set itself to the value needed to conduct the current through the collector. As the base terminals are connected, the second transistor shares the base emitter voltage. If both transistors are the same, T2 conducts the same collector current as T1 does. But the circuit is not limited to create just one duplicate of the input current. You can add even more transistors to create a third or fourth current. And if you need a multiple of the input current, just connect two or more outputs together. But keep in mind that also the sum of base currents increases and comes closer to the input current. This affects the precision of your current mirror, so don't go crazy on the number of transistors. Similar to the current source, the current mirror's output current depends on the voltage at the corresponding output. Fortunately, there are again some tricks to improve the stability of our output current. Again, we want to keep the collector-emitter voltage constant at the current controlling transistor. One thing we could do is add a transistor like this. Hence, the collector-emitter voltage of T2 equals 2 VBE constantly. However, this circuit doesn't work, because we try to force the input current into the turned-off transistor T3. But we don't give up easily and play around with the circuit. And once we swap input and output terminals, the circuit starts working. This circuit is known as the Wilson current mirror, a simple but smart circuit to generate a constant output current. Now we know how we can generate and duplicate a constant current. But many applications require a constant voltage, like analog to digital converters. A very popular circuit to generate a constant voltage is the VBE reference, or more commonly called the band gap reference. The basic idea is to use the base emitter voltage of a bipolar transistor as a constant reference voltage. Unfortunately, the base emitter voltage depends on temperature and changes about -2 mV per Kelvin. But if we add a voltage with a positive temperature coefficient, we can use it to compensate. To do so, we design a current mirror with a resistor R1 connected to one of the emitters. The voltage drop over R1 is the difference between VBE1 and VBE2. Expressing the base emitter voltages by the currents and calculating the difference yields delta VBE, the voltage drop at R1. Delta VBE is proportional to the temperature voltage and thus to the temperature itself. By selecting a certain ratio IC1 over IC2 and one of the currents, we can determine the voltage delta VBE at the resistor. Note that due to R1, IC1 must be larger than IC2. The resistor itself is of course determined via Ohm's law. When the temperature changes, so does the voltage at the resistor, and consequently also the current. Neglecting the small base currents, the output current shares this temperature dependence and can be used to build our band gap. Another resistor R2 is used to transform the current into a temperature-dependent voltage. R2 is selected in such a way that VR2 shows a temperature variation of +2 mV per Kelvin to cancel the temperature variation of a base emitter voltage. Speaking of which, we still have to add the base emitter voltage we started off with. The voltage is provided by transistor T3. As we now have our reference output voltage, we can simply program the current IC1 of our current mirror with R3. But our circuit still needs to be supplied. To keep things simple, we use resistor R4 connected between the supply and our voltage reference. These circuits are called band gaps because for zero temperature coefficient, the output voltage is about 1.2 volts, which is close to the silicon band gap voltage at 0 Kelvin. All of the circuits we studied in this video use 2 or 3 transistors for the principal operation. Being aware of the different characteristics and sometimes quirks of our transistors allow to build really amazing circuits. And who knows, maybe sometime from now there's a video detailing the principle of your circuit. I'm Patrick with the Institute of Electronics. I hope you've learned something today, but anyway, thanks for watching. If you want to learn more about transistor circuits, we highly recommend The Art of Electronics by Horowitz and Hill, as well as Elektronische Schaltungstechnik by members of our institute.